Welcome to our next session. As I have been already advising you, this particular platform is providing us a very good opportunity to learn subject and discuss various things, every part of the concept in a thorough manner, and all experienced teachers are giving live classes. So I advise you to make use of it and tell your friends who are very enthusiastic to attend our classes, and you have got 24/7 doubt clarifying platform also, you can make use of it. So do write the weekend examinations and write to your best ability, and if at all you have got doubts, do interact with us. We are already present on the 24/7 platform. We will be always available for you, either through class, live class, or through mail. We will be in touch with you. So do make use of this particular effective online platform for your very good learning. And coming to the present lecture, in our previous lecture we have discussed different varieties of closed packings. We have got that primitive cube, and we have got HCP arrangement, that hexagonal layers within layers. We have got HCP arrangement, we have got CCP arrangement, and we will just recapitulate what we have done yesterday, I mean in my previous class. So we had this as our HCP arrangement. So this we have done yesterday. This is AB model. This is layer A, this is layer B. A, again you will have B repeated. It is like this, it keeps on going. And this kind of arrangement is called HCP, hexagonal closed packing arrangement. This we have seen yesterday. And the other method is CCP, it is ABC model. Suppose you have a hexagon like this, and the arrangement goes with an octahedral void here. The octahedral void is covered by the next layer sphere, and because of the small change these two patterns differ, and this is A, B, C, again A, fourth one is a repetition of first one, and again you will be having B repeating like this, it keeps on going like this. This kind of arrangement we called it the other day CCP arrangement or FCC, face centered cubic. As I told you, this itself is a unit cell here. You can cut this as a unit cell, or you can take a primitive part of it. See this one. This makes the primitive part. Thus that piece alone will give the primitive cube. In the hexagonal system we have seen primitive also. So this kind of arrangement and this kind of arrangement both have a very important common features. That CCP and HCP have which features in common? This HCP, each sphere is surrounded by 12 nearest neighboring spheres. Means what? Its coordination number is 12. Let us verify how it happens. If you select this sphere, it is surrounded by 6 in its own layer, and these 3 are present on this layer, this sphere. These 3 are also on the sphere. In a way this sphere is sandwiched between these two. So 3 in the above layer, 3 in the below layer, 6 within the layer, put together there are 12 spheres with which this sphere is in contact. So, the coordination number is 12. Coming to this, if you just select this sphere, it is surrounded by 1, 2, 3, 4, 5, 6 and 3 in the above plane, 3 in the below plane. See, this is in contact with again 12 spheres. So, the coordination number here also 12. And the packing efficiency of both spheres is one and the same, because once you are keeping 3 spheres in one layer, whatever may be the case, you are keeping another sphere only on the head of the 3 spheres. Whether you select A type of triangular void or B type of triangular void, you are covering the cavity created by 3 spheres in both cases. But only thing is they differ in the third layer arrangement, that is A, B and A in this case, A, B, C in that case. Whatever may be the case, you are keeping a sphere above 3 spheres. So, the closeness of the packing is same in both cases, and coordination number is also same in both cases. Where do they differ then? Why do you call it HCP? Why do you call it face centered cubic? See, this itself is a unit cell in this particular HCP arrangement. In this arrangement, what kind of unit cell can you cut out? This is not the unit cell completely. If any number of spheres, large number of spheres taking this kind of arrangement, you can get a smaller part as unit cell which repeats in all the directions. The unit cell of this particular arrangement is our FCC unit cell, which we have already discussed in that cubic system. In cubic system, we discussed about 3 varieties of unit cells. One is primitive unit cell, one is face centered unit cell, one is body centered unit cell in cubic system. In that, if you take face centered unit cell, that exactly is the unit cell for this particular FCC or CCP arrangement. So, in FCC CCP arrangement, the unit cell is nothing but what we have discussed in cubic system, that I will draw here. For this, the unit cell is our FCC unit cell. This is going to be the unit cell for CCP arrangement of hard spheres, top, bottom, left and right, back and front. And this is going to be the unit cell for this arrangement, not for this. Now, you may ask how this has got this arrangement. We can easily see that, and here these 3 are in contact, in the sense the right face center sphere, front face center sphere, bottom face center sphere are in contact. So, that makes a triangle, and back, top and back and left make a triangular arrangement. And if you can visualize that unit cell from the corner, one corner, right front corner, see, this makes 4 layers. This makes 4 layers. This is layer A, this is B, this is C, this is D, again A, B, C, A. And if you can check, if these 3, this is settling on these 3, this is a tetrahedral void, and 2 opposite triangles, octahedral void, and here there is a tetrahedral void. So, when you are travelling from this corner to the opposite back corner, you are coming across tetrahedral void, octahedral void, tetrahedral void. So, if you see here, from this sphere to this sphere, if you travel, see, this is a tetrahedral void, this is an octahedral void, this is a tetrahedral void, and from this sphere to this sphere you are travelling, you are coming across that arrangement only, and this particular unit cell represents this kind of arrangement. So, happily whenever you come across CCP or FCC arrangement, ABC arrangement, this is the unit cell, just take it granted. Your cubic system FCC unit cell is the unit cell representing this. Now, what should we do interestingly? So, by the way, how to decide the coordination number is 12 using this unit cell? These two being similar in packing efficiency and coordination number, this unit cell must represent its packing efficiency and its coordination number by unit cell itself. Because unit cell is a representative of the crystal system, you should be able to prove the coordination number is 12 using that unit cell, and whatever is the packing efficiency of this unit cell is the packing efficiency of this, is the packing efficiency of this also, because these two have same packing efficiency, and this is the unit cell of this arrangement. If you can decide the packing efficiency of this unit cell, that is going to be the same packing efficiency for both ABC and AB type. So, let us work on that, on this particular unit cell. So, this is the FCC unit cell. And in my previous lectures, I have done packing efficiency of this, because this has got 4 atoms, 4 spheres, because 8 into 1 by 8 plus 6 into 1 by 2 makes 4. There are 4 spheres. So, 4 into 4/3 pi r cube by a cube. A cube is what? The volume of the unit cell. So, 2 root 2 r whole cube. Why 2 root 2 r? Because A is 2 root 2 r. I think you all remember that this face center atom is in contact with both corner atoms. So, 4 r makes root 2 A. Therefore, A is equal to 2 root 2 r. So, if you work out this, you are going to get 0.74. This I have already done. So, 74% occupancy is there in this face centered cubic lattice, which is a representative of ABC variety of arrangement. We call it CCP arrangement. Therefore, you can conclude in CCP arrangement the packing efficiency is 0.74 and coordination number is 12. Because the packing efficiency of CCP and HCP both are same, you can also tell the packing efficiency of HCP is also 0.74, 74% occupancy is there. That is one thing we have totally concluded. So, now what else we should see? How many, see from this unit cell also you should be able to prove that the coordination number is 12. Means what? Every sphere is surrounded by 12 nearest neighboring spheres. So, let us take, and first of all try to understand the unit cell. In this unit cell FCC, you have got atoms in the corners and faces, and what is the other description? Each face center atom is in contact with its adjacent face center atoms, adjacent face center atoms, because that makes a triangle. This makes a triangle. Similarly, this makes a triangle. See, this is a triangular void, there is a triangular void, in between there is octahedral void. So, what I would like to say, these, once you select one face center atom, that face center atom is in contact with the neighboring face center atoms, adjacent face center atoms. So, this will be in contact with what? Let us again freshly draw. We need a lot of patience to understand all this. So, if I select this face center atom, this will be in contact with top face center atom, back face center atom, bottom face center atom and front face center atom. All the 4 face center atoms it will be in contact, because this face is adjacent to top face, bottom face, back face, front face. So, all the 4 atoms will be in contact with this. In addition, on the right side also you have faces. Top face, back face, front face and bottom face. So, here 4, therefore, and within this it is in contact with all the 4 corners within the plane. Within that particular plane and one face of the unit cell, the face center atom will be in contact with all corner atoms. So, what can we say? This is in contact with 4 corner atoms within the face and 4 of adjacent unit cell and 4 on the other adjacent unit cell in the face center atoms. So, overall this is in contact with 12 atoms. So, the coordination number is 12. So, this way we can prove, and in that particular hexagon form also we can prove that the coordination number is 12 in face centered cubic arrangement, face centered cubic unit cell. Now, our objective is what? Let us now analyze number of voids and sizes of voids in this particular lecture. So, we will see that. Before going to that, first you just have a feel of the spheres. We have already discussed so much, just you can have a visual feel. Now, then something is wrong. Anyhow, we will see the voids. We have already discussed so much about the voids, like suppose you have got 3 spheres like this. This is a triangular void. If you have 3 spheres and 1 sphere on this, this is a tetrahedral void. If you have 3 spheres like this, and in the opposite manner you have 3 more spheres, this is octahedral void. How to locate these voids in a unit cell? Whatever we prove for FCC unit cell is true for everybody. So, let us take one FCC unit cell and first try to locate where you can find the void and how many voids are there and what is the size of each void, that we will have to see. See, all corners have atoms. So, this is FCC unit cell I am drawing. All corners and face centers. Now, where do you find a tetrahedral void? Just now I showed you how a tetrahedral void is formed. 3 spheres on which 1 sphere. This is a tetrahedral void. Where do you find such environment in this? This is an FCC unit cell. We will try to prove here. Very simple. Just see this. I told each face center atom is in contact with the adjacent face center atoms. So, this and these 3 are in contact, they make a triangular entity. There is a triangular void over there, and this sphere is sitting on the cavity of those three. So, you will be getting a tetrahedral void. So, the space in between is a tetrahedral void. So, where is this tetrahedral void present? It is present in between this corner sphere and the triangular entity formed because of the contact of right sphere, front sphere and bottom sphere, that is a triangle. So, this is sitting on these three like that. So, what is the space in between? That is a tetrahedral void. So, if you observe, where does it fall? It is in the space in between. So, that is present on the body diagonal. Similarly, where will you find on the same body diagonal such tetrahedral void? Top face, back face and left face and the corner, and here is another tetrahedral void. So, if you travel on the body diagonal like this, you are finding a tetrahedral void here, you are finding a tetrahedral void here. See, this is one sphere layer, this is another layer. There is a distance between two layers. Somewhere in between you have got the tetrahedral layer, tetrahedral void. And what about other body diagonals? See, this is one body diagonal you have analyzed. On one body diagonal you are finding two tetrahedral voids. On the other body diagonal you have one more. Here also, here you will find one tetrahedral void. Here you will find tetrahedral void. Similar grounds, similar logic. And how many more body diagonals are there? Two more. So, once you take a cube, there will be four body diagonals. So, from here to here, from here to here, from here to here, from here to here. There are four body diagonals. On each body diagonal, there will be two tetrahedral voids. So, what is your conclusion? One body diagonal possesses two tetrahedral voids. There are four body diagonals. So, obviously, how many tetrahedral voids will you find? 4 2s are 8 tetrahedral voids we will find. So, number of atoms are how many in this particular unit cell? 8 tetrahedral voids are present per unit cell, But how many atoms are there in this unit cell? And we have so many times discussed, one face centered cubic unit cell contains 4 atoms. Why does it contain 4 atoms? 8 into 1 by 8 plus 6 into 1 by 2 make 4 atoms. So, there are 4 atoms in this particular unit cell, and per 4 atoms you have got 8 tetrahedral voids. On each body diagonal there are 2 tetrahedral voids. There are 4 body diagonals, 4 2s are 8 tetrahedral voids. So, for 4 atoms there will be 8 tetrahedral voids. Remember this point. How to calculate number of octahedral voids and how to locate octahedral voids in a face centered cubic unit cell. Let us work out. So, we have already done this. This is a unit cell, and we have located tetrahedral voids on 4 body diagonals. So, one tetrahedral void here, one tetrahedral void here, one here. Each body diagonal has one tetrahedral void. So, you are seeing 8 tetrahedral voids. Actually speaking, if you connect 8 tetrahedral voids also, you will again get a small cube there. inside the larger cube you can find a smaller cube arrangement connecting all the tetrahedral voids. I am giving this just for you to make you feel the position of tetrahedral voids. Actually the distance from here to here, corner to tetrahedral void, will be 1/4 of the length of body diagonal, 1/4 length of body diagonal. So that will the tetrahedral void is located approximately at 1/4 length. So what is the body diagonal length? I will come back. Again we will draw, you need to have patience. So there are spheres here. How many spheres are there? 4. Four spheres per unit cell, 8 into 1 by 8, 6 into 1 by 2, and we have seen 8 tetrahedral voids. Now our question is how to locate octahedral void. Octahedral void. What is octahedral void? We have to see this kind of environment. You have to see this kind of environment. Three triangularly oriented spheres and 3 opposite triangularly oriented spheres. In between you have octahedral void. Actually this can be visualized in another beautiful way. Like this, 3 spheres, 3 spheres. See, this is OH void. How? These 3 make one triangle, these 3 make opposite triangle. The place in the middle is octahedral void. See. So whenever you see such environment like this, top and bottom, left and right and back and front, if you see such cross section of 3 mutually perpendicular lines, 3 mutually perpendicular lines, if you find any cross section, you can call it octahedral void. So in the unit cell, where will you find such environment? Left and right, back and front, top and bottom. You have got one space here, and that is octahedral void. So where is this octahedral void present? It is present exactly in the middle of the unit cell, the face centered cubic unit cell. So there is one octahedral void here. Do you find such octahedral voids anywhere in the unit cell? Back and front, left and right, top and bottom, and such mutually perpendicular lines intersecting will give an octahedral void. Now let us analyze in the unit cell completely. I will extend this unit cell. See, like this goes. See, there is one more sphere here on the face of that second unit cell, and I will extend it to the top. At the middle of the face there is one more unit cell, sphere. So if I connect them, I will find one octahedral void here also. See, left and right, back and front, top and bottom. So I can now call this also as an octahedral void. Where is this located? It is located in the middle of the edge of the unit cell. So in the FCC unit cell, every edge center is an octahedral void. I think, and I can give in a more neat manner. We will go in a small unit cell like this. I will extend it to the next. The next unit cell. The top unit cell. If you take, if I take this edge, on this face, on top face and bottom face, this corner is making octahedral. So, you can easily visualize an octahedral void at the edge of a unit cell. So, at the edge of every face center unit cell, you can find an octahedral void. This is octahedral void. That is an octahedral void. But there is a difference between the octahedral void present at the center, the octahedral void present at the corner, on the edge. What is the difference? The octahedral void present at the center completely belongs to this unit cell only, but octahedral void present at the edge, on the edge, is again shared by 4 unit cells. As I told you in the beginning, an edge is always common for 4 unit cells, and you have got an octahedral void on the edge of a unit cell. The edge is shared by 4 unit cells. This octahedral void is also shared by 4 unit cells. We will have to count only 1/4 of that octahedral void. But how many such edges do you have? For this unit cell, there are 12 edges. Top 4 edges, bottom 4 edges, side 4 edges. There are 12 edges. So, 12 into 1/4 gives me 3 octahedral voids. So, there are 3 octahedral voids at the edges, and there is 1 octahedral void at the middle. So, totally 4 octahedral voids are present per unit cell. So, in my 15 minutes discussion, what do we conclude? Every FCC has got 4 spheres per unit cell, and that FCC has got 8 tetrahedral voids. 2 tetrahedral voids present on each body diagonal, 4 body diagonals have got 8 tetrahedral voids. Where is the location of tetrahedral void? A tetrahedral void is approximately located from the corner of the unit cell, from every corner of the unit cell, at 1/4 distance on the body diagonal, and as a result you will find 8 tetrahedral voids completely present within the unit cell. Tetrahedral voids are not shared between unit cells. Octahedral void is present at the middle of the unit cell, which totally belongs to 1 unit cell, and there are 12 edges. On each edge there is 1 octahedral void. That octahedral void is being shared between 4 unit cells. So, 1/4 of that octahedral void belongs to 1 unit cell, 12 edges, 12 1/4 make 3 octahedral voids, totally 1 at the center and 12 on the edges make 3. So, totally effectively there are 4 octahedral voids present per unit cell in a face centered cubic unit cell. So, now we will show both type of voids within the same face centered cubic unit cell. I will draw a bigger one now. Back face, this is front face. So, back face, front face, left face, right face, top face, bottom face. and we have got spheres, all corners, all faces, back face, front face, and this is my FCC unit cell. Now, where do I find tetrahedral voids? See, these three make a triangle, and this, there is a tetrahedral void, and towards the front corner you have a tetrahedral void, towards this you have a tetrahedral void, towards this you have a tetrahedral void. Four tetrahedral voids towards the corners, and at the bottom also 4 tetrahedral voids. As I told you, if you connect all those red spots, you can get one more cube inside, cubical arrangement. That is for just locating the tetrahedral voids. See, how many tetrahedral voids do you have? 4. 4 on top, 4 at bottom. The red colored are tetrahedral voids. Now, where do you have octahedral voids? So, middle is octahedral void, because that is in the environment, octahedral environment, intersection of 3 mutually perpendicular lines. I think I can show you like this, lines connecting left and right, back and front, top and bottom. So, that is an octahedral void, and on each edge you will find octahedral void here. Why is this an octahedral void? Because that is also, you can show like this, you can connect. There is a sphere over here. So, like that everywhere you can find octahedral voids, back and front, left and right, back and front, left and right, every edge is an octahedral void. See, every edge center is one octahedral void. So, totally what do you find? 4 spheres, four spheres, 8 TD voids, 4 OH voids per unit cell in FCC. This information is extremely important. Students should always keep in mind, every 4 spheres in FCC arrangement can generate 4 octahedral voids, 8 tetrahedral voids. Now, in the lattice you do not have only one unit cell, you have a huge number of unit cells, you have a big lattice, space lattice. So, I will just extrapolate. So, the number of spheres double the number of tetrahedral voids, equal number of octahedral voids. So, when I have n spheres can generate 2n tetrahedral voids. N spheres can generate n octahedral voids. So, whenever there is an FCC lattice developed by n number of spheres, definitely there will be 2n tetrahedral voids developed and n octahedral voids developed. This the student should always keep in mind. Now, let us do a very big thing. It is the same arrangement for even HCP. So, this rule holds good not only for FCC, but also for HCP. Remember, FCC and HCP differ in the arrangement of the layers, but the closeness of layers is same, coordination number is same, Therefore, the sphere ratio, octahedral tetrahedral ratio and sphere ratio will also be same. Whatever is true for this unit cell as per this number of voids is concerned is true even for what should I say HCP. So, whenever n number of spheres are making HCP arrangement, 3-dimensional arrangement, you can say there will be 2n tetrahedral voids, there can be n octahedral voids. So, that way you can always be assured. Now, let us work out the volumes of the unit cells and both for CCP unit cell, I should say FCC unit cell as well as HCP unit cell. Volume of FCC unit cell. What is the volume of this unit cell? As you know, in an FCC unit cell, it is a cube, so volume is equal to A cube. But what is A? The edge length. The edge length. Now, how A is related to radius of the spheres? As I told you, if you draw this outside, you will have this kind of arrangement. So, this will make 4r. 4r is equal to root 2a as per Pythagoras theorem. So, a is equal to 2 root 2r. Edge length is given by 2 root 2 times the radius of the sphere. So, what will be the volume? So, volume is equal to 2 root 2 r whole cube. This gives me 16 root 2 r cube. That is the volume of the unit cell in terms of the radius of the sphere. How to calculate volume of hexagonal unit cell? Let us see and work out. Remember this 16 root 2 r cube. Hexagonal unit cell means what? It will be like this. I want the volume of this unit cell. How to calculate the volume of this unit cell? Very simple logic. Actually, there can be methods like you calculate volume of this triangle, and there are 6 such triangles, multiply with the height. Calculating the height is a tough task. Instead, we can go by a simple logic. If I can make an FCC out of similar sized spheres, both have same packing efficiency, both have same coordination number. How many spheres are there in this unit cell? Let us calculate. So, this volume is occupied by 4 spheres, because in FCC unit cell we have got 4 spheres effectively. So, effective number of 4 spheres are enjoying 16 root 2 r cube volume. So, here how many unit cells are there per how many atoms are there per unit cell we will calculate. The corners are 12. See, this corner is shared by 3 unit cells here, 1, 2, 3, and above 3 means what? Every corner is 1 by 6 in a hexagon. So, how many such corners are there? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. There are 12 corner atoms. So, 12 into 1 by 6 makes 2 atoms, and you have got 2 face center atoms. Each face center atom is half. So, 2 into half makes 1, and there are 3 spheres inside the hexagon, a little inside. They are not being shared by nearby unit cells. So, what can you conclude? These 3 totally belong to this 3 into 1, 3. So, put together there are 6 spheres per unit cell with the same closeness like this. 4 spheres having this much volume, 74% occupancy, 6 spheres with same 74% occupancy will have how much volume? That question I can simply ask, because it is a proportional packing efficiency. This is the effective volume for 4 spheres, and there are 6 spheres here with the same closeness of spheres. So, what is the volume of that? So, we will work out. 4 spheres having 16 root 2 r cube, 6 spheres have how much? So, 6 by 4 into 16 root 2 r cube, this goes 4 times, 24 root 2 r cube is the volume of HCP. So, volume of HCP unit cell is 24 root 2 r cube. This volume of CCP unit cell, and this is the volume of HCP unit cell. Let us work out the same result in some other method. See, density is what? Mass by volume. For FCC unit cell, what is the density? There are 4 atoms in unit cell, and each atom has m by n naught atoms like mass, and volume of HCP is what? Volume of FCC 2 root 2 r whole cube. So, this is the density of FCC unit cell. What will be the density of HCP unit cell? There are 6 atoms per unit cell we calculated, and each atom has m by n naught mass, and I do not know the volume. And as per closeness is concerned, as per density is concerned, both will have same, because identical spheres having 74% packing efficiency must have same density. So, these 2 densities must be same. So, what I would do, 4 into m by n naught 2 root 2 r whole cube is equal to 6 m by n naught VHCP. So, n naught and n naught get cancelled. So, m and m get cancelled, this 2 times, 3 times, and you are going to get VHCP as 3 into 2 root 2 cube. This is 16 root 2 r cube by 2. This 2 goes 8 times. So, I got 24 root 2 r cube. So, however you calculate, volume of a HCP unit cell is 24 root 2 r cube. This is as simple as this. Definitely the volume depends on the radius of the sphere. If you make HCP unit cell with footballs, if you make a HCP unit cell with table tennis balls, the volume will not be same. So, the volume depends on which sphere you are taking. So, this is the volume of HCP unit cell. Now, coming to sizes of the voids, we have now located where the voids are present, and now let us work out on the size of each void. Let us take triangular void. This is a triangular void with 3 spheres. You can connect the centers like this. So, you got a triangle like this, and the edge of the triangle is making 2 r's. So, this is 2 r, this length, each edge is 2 r. And I would like to know a small sphere's radius. that is void, that darken one is the void. I want the radius of that, let it be small r, radius of this is big R, capital R. Now if you see carefully, see like this, if I keep a small sphere here, this distance makes what? Capital R plus small r, because there is a small sphere here, there is a big sphere, put together is capital R plus small r. So that falls here, somewhere at the center of the I can say centroid. Now what is this height? Let the height be h, and again what is this 2r? What is this r? So h square plus r square makes 4r square, h square is equal to 3r square, h is equal to root 3r, h is equal to root 3r, means this height is root 3r. But we do not want that height completely, we want only this part of the height, the major part. The centroid divides the vertical line in 2:1 ratio. In any fundamental mathematics everybody knows. So I should take the 2/3 part of the height, 2/3 part, 1:2, 1:2 means what? 2 parts of that, 1 part of this. 2/3 part of the height will make r plus r, this height. So what is the total height? Root 3r, in which I should select 2/3 height. So 2/3 height of root 3 r gives me capital R plus small r, and this root 3 goes root 3 times. Now I have got, I will divide everything with r, r by r, r by r and r by r. So this get cancelled, this gives 1. So small r by capital R is equal to 2 by root 3 minus 1. So that is going to give me approximately 0.15. So the small r is nothing but 0.15 capital R. What do you understand from that expression? The radius of a sphere you keep in the triangular void will be 0.15 size that of the radius of the sphere in which you are keeping the small sphere. So this is the size of the radius of triangular void. So it depends, if you keep footballs and make a triangular void, that size into 0.15. If you keep small table tennis balls, 0.15 into r, you will get small r. So this is how things will move. Now let us think of tetrahedral void. Suppose I have a tetrahedral void like this, the in between place is tetrahedral void. I want the radius of that small sphere exactly fits into tetrahedral void. How to calculate that radius? So first of all let us take a fact, we will take an FCC unit cell. In that FCC unit cell, as we have discussed, the tetrahedral void falls 1/4 from the bottom, 1/4 of body diagonal, 1/4 distance from the body, from the corner possesses the tetrahedral void center, center of the tetrahedral void. So what is the body diagonal length? Body diagonal length is nothing but root 3a. In any cube, body diagonal is root 3a, very simple logic. This makes a, this makes root 2a, obviously this will be root 3a. So, body diagonal is root 3a, out of which you should cut 1/4. That 1/4 will have what? That big sphere and small sphere. Big sphere is the one which is making the unit cell. Small sphere is the one which is occupying in the tetrahedral void. So, this makes my capital R plus small r. And what is A in an FCC unit cell? Many times I told you, A is 2 root 2 r. A is 2 root 2 r. How? Because in a FCC unit cell, the face is made up of this arrangement. So, if you connect these 4r is equal to root 2a, a is equal to 2 root 2r. So, in place of a, I can keep 2 root 2r. So, let me come back. So, capital R plus small r makes 1/4 of the body diagonal. So, root 3 by 4 into body diagonal is A is given by 2 root 2 r. Now, this goes 2 times, this goes root 2 times. So, I am going to have root 3 by root 2 r. This is capital R plus small r. Now, divide both sides with r. So, you will be getting r by r plus r by r is equal to root 3, 1.732 by 1.414, and it is going to give me 1 plus small r by capital R is equal to somewhere around 1.225, this value. So, r by r is equal to 0.225. So, r is equal to 0.225 into capital R. So, this is the story. The tetrahedral void is 0.225, that of the radius of the sphere making the void. So, if you have a sphere with in contact with radius r, if at all you have a tetrahedral void here, that will be 0.225 capital R. Radius of the tetrahedral void will be that much. So, now let us work out radius of an octahedral void. Now, you know the location of tetrahedral voids, you know the number of tetrahedral voids, you know the size of tetrahedral void, you know the location of octahedral void, you know the number of octahedral voids. Now, we will work out the radius of octahedral void. Where is octahedral void? Where do you find an octahedral void? Just now I told, at every edge you have an octahedral void, and in the corners you have spheres. See, if you take an edge in a FCC, there will be a sphere here, there will be a sphere here, there will be octahedral void here. Rather, you can write like this: exactly fit void. This is OH void, and these two are making the edge length. Total edge length is what? This is A. This A is divided into how many radii? This is one radius, capital radius, this is one capital R, 2 the radii of the big spheres, and this is a diameter which makes 2r. So, A is equal to 2 into capital R plus small r. This is satisfied in FCC. Now, we know pretty well again A is equal to 2 root 2 r. I proved it many times. In case of FCC, A value is given by, edge length is given by 2 root 2 r. So, 2 root 2 r is equal to 2 into capital R plus small r. So, I will cancel out 2. What am I having? Root 2 r is equal to capital R plus small r. I will divide with capital R. I will get root 2 is equal to r by r plus r by r. This gives me 1, this gives me 1.414. R by r is equal to 0.414. So, r is equal to 0.414 capital R. This is going to be the radius of an octahedral void. So, let us put everything at one place so that you will have a clear cut idea. AB, AB, AB or ABC, ABC dot dot. This is HCP, this is CCP. In both coordination number is 12, coordination number is 12. In both packing efficiency 0.74, 0.74. That will always be there. The side of a radius of a triangular void 0.15, that of the sphere making it. Radius of tetrahedral void 0.225, the sphere making it. The radius of octahedral void 0.414, the sphere making it. These things you should always remember. And whatever may be the arrangement, out of n atoms, you will be getting n octahedral voids. Out of n atoms, you will be getting 2n tetrahedral voids. This also you should remember. And you know the number of voids per unit cell, you know the size of voids, and you know the location of the voids also. Location of the voids means what? In FCC unit cell, on the body diagonal you will have 2 tetrahedral voids, on the every edge you will have octahedral void. Why should you locate? We will learn the importance of that in our next class, but in the meantime we should just focus on even a body centered cubic arrangement. In a BCC, as you know the unit cell, the coordination number will be 8. The coordination number, see there are 8 spheres around each sphere. Of course, there may be some interesting features like who is the next nearest spheres. In the next unit cells, go to the next unit cell. So, this is the next nearest. How many such next nearest pairs will be there at every unit cell? So, this is also at the same distance, and you have got 6 faces and 6 such nearest neighbors. So, the first neighbors will be 8, the next neighbors will be 6. Like that we can keep on calculating different varieties of coordination numbers. But here no such well defined octahedral voids and well defined tetrahedral voids you will not see in the BCC structure. So, those voids are well defined. This kind of close packing you cannot see in, means they will not be in contact in BCC lattice. You can find such arrangement only in HCP and FCC lattices. So, what for we have learnt all this? So what? You have learnt some FCC unit cell and all. So what you are going to achieve? Now what we will do? We will use these structures and we will assume some ions will adopt that structures and the other ions would occupy the voids. We call it limiting radius ratio. So how to understand sodium chloride structure, cesium chloride structure, zinc sulphide structure, calcium fluoride, lithium oxide, diamond, how to know the structures of those materials. With the basic knowledge of these arrangements, primitive cube arrangement, BCC arrangement, we have FCC arrangement and HCP variety of arrangement. These are all references for the arrangement of spheres, and we know the limitations of the gaps present in between, and we know the locations of voids. Keeping them in view, we will try to explain the structures of different materials, different crystal substances, crystalline substances like your rock salt, sphalerite, woodsite and fluorite, calcium fluoride, ammonium bromide, magnesium oxide. See, these are all arranged in a nice crystalline manner. So, some make the lattice, the others may occupy the voids. All such things we have to discuss. So, in order to explain the crystal structures of various metallic, molecular, atomic, I mean to say that network solids and ionic solids, we take the reference of these close packing arrangements. So, we will now work out how good we can use these arrangements for understanding the crystal structures of various substances in our next session. So, in the meantime, keep thinking of all these things, just keep on seeing the recorded version. Whatever I speak repeatedly, you make a note of it and you also get used to it. Voids, number of voids, size of voids, location of voids, everything you also work out, so that your job to solve problems in solid state chemistry will become very, very simple. We will try that in our next session. Have a good day. Thank you.